by Brustein, and he will tell us about the outside and inside views of black hole entropy sourced by the string winding condensate. Take it away.
Thank you. First, we really do that, but thanks for having. Okay. So, because of the wonderful and clear presentation that Yiming just gave us, I can save a lot of time. But my talk would have some overlap with the previous talk, but it's not complete. The overlap is smaller than I expected. So the idea that I want to present is that black hole microstates are long strings. So in a way, it's an old idea, but you will see that it's related to the old ideas, but it's in many ways new. And the way I want to communicate this message is by try to convince you that the winding condensate that Yiming talked about is the entropy density of the string, or the number density. So you should, if I'm successful by the end of the talk, you would understand that this chi star that Yiming was talking about is really describing the density of strings in space. Now, it's not quite the density of strings because chi and chi star go back and forth. That's why they don't have the string charge. And so it's the sort of the absolute value of the string density. Okay, so, and I will use the same HP or a thermal scalar EFT. These winding modes are many times called thermal scalar because they are coming from wrapping the thermal cycle. And then most of my discussion would be about the entropy of black holes, about how to compute it in this context. And then at the end, I will essentially explain how I think the Horowitz-Wolczynski idea can be improved by including interactions. And Joseph, in this case, the interaction will actually answer in the positive your question of growth. So, and it's not just growth, but you have to have a solution for each mass. And that solution has to be larger than the other ones. So and you will see how this comes about. So, and if I have time, I will end with something which is in a way even more surprising, and that's a classical solution that mimics the properties of these string balls. Okay, so let's see. So this actually was covered to a certain extent by Yiming, so I will not go over it. But the main point here, as
Is the microphone off?
I don't like this.
I can hear now.
Because then my hands are. Okay. So we continue in the hope that the technology keeps up. Yes. So, and just to sort of frame this, the thinking, here is a free string that Yiming was talking about. Think about it as a random walk, it's an old idea. So its size, its spatial size is the square root of its length. When you put it in the bounded region, the size decreases compared to the free size. This was discussed here, but still the configuration space is dominated by long strings. You can actually find the distribution of lengths. Now, when you add string interaction in the form of joining and splitting, what happens is that this free string shrinks even further and creates a spherical region. In that spherical region is supposed to be the black hole. This is something that in polymer physics is well known and got 2 Nobel Prizes, one in 74 and the other one by Dejean in a year that I don't remember. And the idea is to get the fact that you have entropy that is extensive is special to weakly coupled theories. In polymer physics, you can get any type of relationship between size and entropy. It's like anomalous diffusion. And it depends on the nature of the interaction. If the interaction is repulsive, you get super extensive. If the actual interaction is attractive, you get sub-extensive. And depending on this factor, this Flory exponent, you can also get to area law. So from that point of view, an area law of a black hole entropy is not very special. Okay, so this is the plan of my talk. When did I start? 10 after? Okay. So I will describe the effective field theory, compute first as a magic trick the entropy of black hole, and then maybe a better explanation by using a 2-dimensional well-known CFT to show that this magic trick is probably correct. And then I will discuss the Lorentzian interpretation using interactions. Okay, so again, repeating very quickly Yiming's what Yiming already said, that we compactify on the thermal circle, the size, the circumference of the thermal circle is essentially one of the temperature. You have plus and minus 1 winding modes that become massless at the Hagedorn temperature, and the Euclidean path integral actually computes correctly the partition, the free string partition function at the Hagedorn temperature. Now, so let me now take this Horowitz-Wolczynski theory, which you already saw. The difference is that I will call GTT e to 2 sigma and not e to the 2 phi, as Yiming say. I'm sorry about that, but I couldn't change it. And the mass of this complex scalar is positive. Mass square is positive below the Hagedorn temperature and negative above the Hagedorn temperature. That negativity just says that we need to look for another solution. What I will do is include interactions and find a place where the mass square of the scalar would still be positive. Okay. But we don't discuss that now. And these are abbreviations that I will use throughout the talk. And okay, so and this, since I'm working in type 2, I already put the value of the Hagedorn temperature like so. The 2 is related to the fact that it's 2 square root of 2 in type 2. And this is what you actually, when you look at this theory and find solutions, you just look at solutions, classical solutions of the theory, you find that Chi star, this condenses. It's proportional to epsilon square. The value of the condensate is proportional to epsilon square over kappa square. Kappa square is the gravitational constant, and the length here, where the space-time deviates from flat, goes like 1 over square root of epsilon. This is in the original Horowitz-Wolczynski description, and this picture is similar to what Yiming showed. And now I want to use this simple theory. And as I said, it's a magic trick. I want to show you how, from this theory, I compute the black hole entropy. So I take out the lambda, the cosmological constant. I use an ansatz for the metric, which is spherically symmetric. Tau is the Euclidean time. It's periodic with this periodicity. And this theory has a asymptotic Schwarzschild solution with chi going to 0. Beta, the circumference of the thermal circle, is R0 over d minus 3. I do it for every d. Little d is the space. And we start with that. We write the equations of motion, right? We have 4 equations of motion. One for the complex field chi. Where is it? Here. For GTT, which I parameterize as e to the 2 sigma. For a combination, a linear combination of the dilaton and the G mu nu equations in the usual way. So here is essentially the traceless part, and here's the trace part. Okay, it's completely standard. Again, now the entropy is given again in a standard way, beta d beta minus 1 of the action. Actually, observation by Yiming and Juan, which we should have noticed a long time ago. We identified Chi star as the entropy, but we didn't relate it to this formula. And so here you see, even at the classical level, we get an entropy because of the no local term in the HP action, which goes like beta squared, because beta is the circumference of the thermal circle, and the string winds around the thermal circle and gets an energy that's proportional to circumference. This is a non-local term, and it gives rise to an entropy of this form. Now I use the sigma, the GTT equation of motion, equal to chi star times e to the sigma. I plug it in here, and I get S as a total derivative of something that you can think of as a current. Okay, and so I can integrate by parts, and the contribution comes from the boundaries of space. One boundary is at infinity, and what I will assume that there's no contribution from the inner boundary. I will try to justify that later on. And then, okay, so I assume that there's no contribution. We call it puncture boundary conditions because of reasons that will become clear later on. So the only contribution is coming from the asymptotic region. And we know how the asymptotic region behaves. We plug in the asymptotic behavior, and we get the full exact entropy of the black hole. Okay, so that's the end of the magic trick. So this is, yeah, the question was, how would alpha prime correction modify this relation? So here at this level, they could modify the relation by order 1 or even more, okay? But if they don't modify these boundary conditions that I mentioned, then I expect the result to hold. And as we discussed in private, we have some work in progress showing that the alpha prime corrections are probably, and G string corrections are probably much less important than you might imagine. That's why I called it a magic trick, because it could go wrong in many ways. So this is what you pointed out there. The winding number as the thermal circle shrinks becomes ill-defined. You could add a very long list of possible ways, but still it's interesting that it gives you exactly the value. So maybe there's something into it. Yes.
Polchinski solution has the same form as the Bekenstein-Hawking entropy in the regime where it is valid?
This actually is not the Horowitz-Polchinski solution. The Horowitz-Polchinski solution was, if you remember, it was something that had a width of 1/√² of epsilon, and chi star was epsilon over kappa square. So here, it's another solution to the Horowitz-Polchinski action, allowing the thermal circle to vary much more, in a much more significant way than the Horowitz-Polchinski solution.
So I guess I'm confused as to what you're looking at. So in the solution for which gives Bekenstein-Hawking, is the thermal circle pinching off somewhere in the geometry?
So hold on with this question, because I'm coming to a description of the geometry. Here, I didn't describe the geometry. I just said that I need a dr sigma. So in addition to h going to 0, I need H prime or GTT prime, dr GTT to vanish, which is different than, but so let me show you now in this 2D example, how does the geometry look like? And if you're not satisfied, repeat the question.
Okay,
Okay.
so, but
It's
let's
not, in this case, it would not be the standard Euclidean cigar. It cannot be.
okay. But the thing that you presented, let's see, remind me what the assumptions that went into it. You assumed that there was no contribution from except at the asymptotic boundary?
Yes.
Okay,
That was the only thing that went into it.
okay, thanks.
But that, of course, requires the geometry
To cooperate.
to cooperate. And this is what I would like to show you an example where things are under control with geometry and actually cooperate. And I would argue that this is something that I view as necessary or generic, if you wish.
Okay.
Hmm? So you actually start from
infinity.
since
No, I mean, at infinity, you are near the Hagedorn temperature.
no.
How can you use the Horowitz-Polchinski thing then?
So I didn't, well, it's here, right? So I'm actually at infinity. I'm starting with a large, so the Schwarzschild radius of this black hole is large. So I'm much further, I'm at temperature that is very different from the Hagedorn temperature. Then the geometry shrinks, you get, and the winding condensate builds up.
Mhm.
You will see that explicitly next. It
Okay.
builds up, and then the geometry cooperates. And when you integrate over that buildup from 0 to infinity, you get the entropy.
Even if this Lagrangian is officially not valid at away from, because you know the Horowitz-Polchinski
Well,
action
it's
is only
in
valid near the Hagedorn temperature. It's not valid far away.
Yes, but in this case, this Chi star becomes very massive, and it actually goes to 0. So
It doesn't matter. I see. Okay.
yes. So here we will see some more details about the geometry, but the main idea is that this entropy should be viewed as a charge. And so it's really should be sensitive only to boundary issues. I'm not sure I will be able to actually demonstrate that, but okay. So now what I do something similar, but my starting point is a 2D theory, well-known SL2 module 1, which is related to the 2D black hole. You can think about it as some dimensional reduction if you, like me, don't like very much 2D. But you can, it's okay to think about it as a 2D example. Again, here we start with a beta that is much different than the Hawking temperature. And as we go in, this thermal circle shrinks, and here it becomes similar to the Hawking temperature. That's the well-known solution that corresponds to this to the CFT. And the cigar is characterized by a Rindler-like line element at the tip. Okay. So now I write the same action that I wrote before in 2D. And the metric, I take it to be like so. So this is GTT, G tau tau. And I'm using coordinates where GRR is 1, tau is periodic with a period of beta, and beta is much larger than beta h. Okay, and this is related to what Josip was saying previously. And to do that, I need k, the level, to be much larger than 1. Okay, now, again, something completely standard. I take this action. I calculate the equation of motion, the 4 equations corresponding to the, this is the GTT, G tau tau equation. This is who knows what. And so, but there are 4 of them. So exactly like before. An interesting phenomenon that happens here, which we're not absolutely sure why this happens, is that we can reduce the second order equations here in a system of first order equations, which was a surprise to us. We discovered it by looking at the solutions numerically. And let me focus here on this equation, which has a very nice interpretation, which I think also you pointed out. And this is right. If chi prime equals minus h chi, I can write a solution, formal solution for chi in terms of an integral of h. And this is just the area of the world sheet here. So chi, I mean, it's the color coding here shows the amplitude of chi. So it's larger at the would-be tip and decreases as beta increases because the mass becomes bigger. And so it dies away. And you can see here that essentially, so chi star, you can see that it's related to the amount of string we have. So it's a nice nice result resulting from this first order equation. And I can now look at the solution of the equations. Okay, so what I do is I look analytically, I look at the solution, the asymptotic solution for rho. Rho is the radial coordinate. Remember, the S square is h square of rho d tau square plus d rho square. So rho is the asymptotic coordinate and it should match, in this case, the SL2 cross U1 solution without winding. And it does, of course, like so. Okay, so that's not a big surprise, but a surprise is that we have another branch of asymptotic solution. Not here is rho larger than square root of k alpha prime. So that's the curvature radius, but here it's rho much smaller than minus square root of alpha prime. And we get an asymptotic solution that behaves like so. And the two solutions connect to each other only for a specific value of the amplitude of chi. And that specific value is, as I show in the next slide more clearly, is the value that is predicted by string theory. And it's a very special number. It's e to the minus Euler constant divided by 2. And we discovered it numerically. Here, this is e to the minus gamma over 2 is this number, which we were able to see numerically from the solutions. It's very strange. And so this is the asymptotic side. square root of alpha prime over rho. This is the other asymptotic side, which we cut off. And here, this is h of rho versus rho. So it's, think about it as the radius of the thermal circle. And you see that it behaves differently for different amount of chi star. If chi star vanishes, you get a cigar tip like the solution, DSL2 module 1 solution that ends here. For A that is less than A critical, we get this, you see this black solution that ends much further. And at A equals AC, the solution goes all the way to infinity and only pinches off there. So both H prime and all the derivatives go to 0. So it's like a very thin, long tube.
Excuse me, can I ask a question? Can I ask a question?
For values of the amplitude that is larger than the string amplitude, the string predicted amplitude, we get a singularity at a finite place. And these are the boundary conditions, you remember, that I needed in when performing my magic trick. So here, string theory tells us that back reaction, non-perturbative back reaction, creates the geometry such that the magic trick works. Yes.
Masaki, go ahead.
Can you hear me? Hello?
Maybe
we cannot hear you.
Why shouldn't let him type it in the chat and then you repeat it?
Can you type it in the chat?
Okay, so let me go on for a while until the. Yes, sure.
Masaki's question is, what is the relation between this solution and the cigar solution?
This is the cigar solution. The
blue one.
The blue one is a cigar solution. As you add more winding condensate, you go closer and closer to this asymptotic solution. So nice. The geometry,
gets longer.
The geometry changes. The geometry changes by the back reaction of Kai-Kai star.
And Masaki is asking, are you saying that the cigar solution isn't really correct? Because it
cigar
ignores...
solution is correct without without a winding condensate. But if you add winding condensate non-perturbatively, you take the back reaction. It's not that it's not correct; it's modified.
No, but I mean, in a physical system, you know, that's.
Well, it depends on if you add the winding condensate. So his point is that is no longer the solution. You get a different solution.
And you don't have a CFT anymore. So Masaki is saying that the cigar is an exact CFT. So
yes, but the point is that CFT has exact marginal operators that, as I will show, that you can add them and they correspond to the solution.
Okay.
So it's really a back reacted cigar, but the back reaction is in a way big. Yes.
And the question is this new solution a cigar CFT deformed by vertex operators corresponding to the winding mode?
So wait for the next slide.
Okay.
So if I take this HC that you have written over there and take rho to infinity, not minus infinity, naively it seems like it gives me a signature which is -1 + 1.
No, this is what you get. It joins smoothly to this asymptotic, the asymptotic cigar.
This HC is when, so could you explain this HC again? I missed that part.
There's
HC.
There's a special value of A. A here is a free parameter in the EFT. Okay, we cannot fix it. What we see is that there are three phases, if you wish, depending on the value of A. One of them is this phase that is delimited. So it's the blue, which transforms into a black and then another black and so on. That ends, you see, it ends here with something that looks like a cigar tip. Okay? And then when AC, and then when you increase A, increase the value of A, you get a singularity. This is the red curve here. Okay? And at AC, which we were actually playing around in able to get something like 15 digits. I'm not sure if it's correct, but that's how we discovered that this is e to the minus gamma over 2. And at this point, the two asymptotic solutions that I described are joined, and you see that the geometry is changing by a significant amount near, I would say, the geometry, the interior geometry or the near horizon geometry is replaced by a stringy geometry. Okay, so, and these are the solutions for the other fields. You can see, I mean, you can just look at them, everything is finite. And this is the CFT discussions, right? This would be the original CFT. And then these are two truly marginal operators that you can add. This A corresponds to the amplitude of chi, right? That's the vertex operators of the winding mode. And this is for the tau-tau metric. And my collaborators who have worked on this problem for many, many years, as you probably know, because you were able to actually calculate this parameter using these type of expressions. And large K, you remember, it's the one that tells you that we're looking at a large black hole with small curvature. The limit of this is exactly e to the minus gamma over 2. Okay, so basically what we see here is you can call it topology, which is actually, if you calculate the Euler character of this quantity, is not that of a cigar, but is that of a cylinder. And the geometry here is replaced by a long neck, like so, infinitely long in the coordinates that we used. And it removes the obstruction for a transition between something like the Horowitz-Rolzynski and a black hole, because the Euler character or the Witten index of these two solutions, the black hole and the string winding modes, are the same. Okay, but the way it did that, it needed to have large back reaction. Okay. So let's calculate the entropy. Now it's less of a magic trick, because we know that the EFT corresponds to a CFT, so a real string solution. And I just, again, compute the classical entropy by taking beta dd beta minus 1 of the action. Same expression as before. The the G tau tau and phi equation and dilaton equation of motion combined gives me this type of total derivative that is equal to this quantity, just as before. Now we know for sure that H prime at the inner boundary at infinity vanishes, so there's no contribution from the inner boundary, only contribution from the outer boundary, where we know when we get the expected exactly the Bekenstein-Hawking entropy in 2D. Okay, so by now you should be convinced that chi square or chi absolute value square is the entropy density. Yes, so again, there must be some reason that this theory works better than expected. And we are now with Yoav Zigdon, my excellent student. We are working on understanding that, and this will in some ways explain why this the theory calculates better than expected. And what we find, not yet completed, but should be completed soon, is that the entropy is a topological quantity, it's a nether charge, and so it's protected. That the puncture is required for ensuring the U1 winding, which the string theory has in any dimension, compactified on the thermal circle. And the EFT should respect that. And we also find that if we add branes, so to charge up the black hole, these calculations work, including up to extremal black hole, and it works in also in something that looks like a magic trick, because in that case you also get a contribution from the flux or the branes, you get a contribution also from the horizon, and it exactly cancels the whatever it needs to cancel, such that the total entropy is the entropy of the black hole. So we were able to reproduce the entropy of all the Horowitz-Strominger solutions plus more. Okay, so how am I doing in time? 10 minutes? Okay, I will take some more, probably. Okay, so now to the part which actually this was our starting point. That's how we got to all of this. So now, if we accept that the winding mode condensate is the entropy density of the string, then we can, you probably cannot read this, but I will read the important part to you. So once you understand that the chi star is the entropy density, it's possible to include interactions in a way that I think is better, and it will fix that mass radius relation if considered. And see, the reason why Horowitz and Polzinski, it's very, I was very sad that I couldn't ask Joe about that, because when I read this, he was already not with us. And so they said is that because gravity is long range, you see they say it's a subject of polymer physics, but they said that the interaction is non-local because long range, and long range polymer physics was not studied. But if you think about the string interactions, they are local. If you don't integrate over the heavy mode, you just think about joining and splitting, they are local for the string. So you can include them in a very simple way by essentially add a term which we can calculate. It's there. We can calculate by, and we calculated with Yoav. This was also calculated by Untitled and somebody else, and also by Igor and some people a long time ago. This is just, you can calculate that, the coefficient of that from the S matrix of 2 to 2 of windings, which we did in type 2 and the bosonic string. And that coefficient here comes out to be, you see, 2 kappa square of alpha prime. So think about string interaction or polymer interactions. The first one is just E minus ST, the free energy. And the second one is just the strength of the interaction. That's proportional to the number density square. Okay, and you can calculate that, and we can show that if chi star, this requires that is slightly higher than the Hagedorn temperature. So this term is negative. The mass is negative, and this is positive. So you have a potential that goes down and up. And if the string density is small, you can convince yourself that corrections, alpha prime correction and G string corrections are also small. So these are the dominant terms. And we can calculate thermodynamic quantities using this expression, identifying chi star with the string entropy density. And what we find is something that is already in the Horwich, in the Attic-Witten paper, that we find a Peebles rho. And this corresponds to S equals square root of rho, which is the maximal entropy. It's the maximal possible entropy. This equation of state P equals rho is actually quite strange, because this is in in any dimension. It's not in 2 dimensions. It's a equation of state of radiation, but in higher dimensions, something that you might imagine doesn't exist. But here, because these are strings, somehow they can do that. And this actually is already in Attic-Witten. They don't write it explicitly, but their free energy is proportional to T square. And if you do that, you see that this is the equation of state. You find, and this is very important observation, that it's a desaturate the entropy bound. Now, and again, you can just do the calculation and find that P equals rho. And what this means is if the temperature varies as 1 over R, which is something that, I mean, we haven't yet calculated from equations, but it's very reasonable. You find that you find how the pressure and the energy density vary. This is in any dimension, right? It's not restricted to 4 dimensions. This 1 over R square is in any dimension. And in this case, you find, just like in polymer physics, you find that the entropy and the energy of this condensate scale exactly as a black hole. And as I said, in polymer physics, if you have the correct interaction, you can get that. So here, the key is here that the temperature goes like 1 over R, which, as I said, it's something that we imposed here to get this relationship, but I think you can prove that this is a result of an equation. So, okay. So the picture is the original picture. We have a ball of string, because of interaction, its size decreases from the free size to the point that it obeys the mass radius relation of a black hole. Interactions are important because they allow the string to cut and be smaller, otherwise it cannot get smaller. And it obeys the mass, and it has an entropy, which is just the string entropy. Okay, good. Now, when, of course, in that, from this point of view, there's no classical geometry. In fact, the geometry is fluctuating a lot because the entropy is maximum. So when I was giving this talk, people asked me, okay, but what is the geometry? So eventually we came up with something which I think is actually interesting and very useful if you want to calculate observables. In this string ball, you remember each sphere has the entropy of a black hole. So each sphere is like a black hole. That's why it doesn't collapse, because it cannot. So maximal entropy, it cannot become smaller. Otherwise, the entropy bounds will be violated. And it turns out that in this case, if you parameterize the energy momentum tensor like so, you find a solution where both these f's vanish, right? So each sphere is a solution, and that actually, and rho goes like 1 over r squared, p transverse is 0, f is 0, and p equals minus, p radial equals minus rho. And that object is, if you wish, equivalent for an outside observer that doesn't care about entropy. It's equivalent to the p equals rho maximal entropy solution. And this solution is actually stable. We checked that linearly, but that's much more than, so in a way, it's similar to the Grabastar or what Wolf was saying, but the symmetry, so it's p equals minus rho. That's how collapse is prevented, because in the singularity theorem, that's the combination p plus rho enters. And in this case, it's actually stable. We can check that. And it's both, yeah, so it's stable and hydrodynamically stable. And that's it. Thank you.
Okay, we have time for the questions before the discussion session. Where's the ball or the cube? Oh. Well, yeah.
Yes.
Some questions about this modified cigar solution.
Yes. So I go back to the which slide you should tell me.
So your collaborators calculated the 2-point function in this cigar background using the exact worldsheet conformal field theory. And that's reproduced by the cigar geometry without your modification. And so I'm curious as to how your collaborators are happy with this modified geometry, because it seems like it would spoil the exact 2-point function agreement between.
Yeah. Okay. Since you know them, you know that if they weren't happy, they would express that very openly. So if you are worried about whether they're happy or not, they are happy. This is something that I don't have an obvious answer at the moment, but I can ask them. I think the thing is that these calculations are tricky because in this case, you have to do them again in this background and see what you get. And there are many surprises here. This think this.
Well, if I take your naive solution with this tube running off to infinity, I mean, stuff can get trapped down that tube for an extremely long time before it reflects back, if it reflects back at all.
So I think they did calculate, for example, the reflection coefficient in this kind of thing, and it does agree. The full reflection coefficient does agree. I must say that, I mean, I trusted them on this part, so I'm not sure how to answer this question very effectively, but I can sort of communicate your questions to them and see what happens. You can also ask David.
All right. Well, without this spike coming off the end, the reflection coefficient is reproduced by a combination of the dual Liouville theory and the cigar
Yes,
geometry.
so I think the idea is that this is a manifestation of the FCZ correspondence or duality or what have you.
So the other question is, in the transition region near the tip,
Yes.
if I understand that you're modifying the geometry, roughly speaking, at the string scale from the tip.
Yes, so we can, let me put up that slide.
Basically, that's good enough,
Yes,
right?
yes.
So I'm assuming the vertical axis is like string scale, right?
Yes,
In
yes,
string
this is
units.
in
Right, so
string
you're
units.
basically within a radius of order half a string length, you're changing the
Yes,
geometry.
yes.
So should I worry that the curvature of the geometry is large?
Yeah,
right
this
where
is
you're joining the two?
you should.
And so what
And-
about higher alpha prime corrections to this geometry?
Yes, so let me just, where is it? Right, so yes, so in fact, in this case, so I can tell you what my understanding is, that there are large alpha prime corrections in this region, in this transition region.
Right.
So initially, they don't matter. There is a region near the tip of order string lengths, 2 string lengths, and so on, where the curvature becomes large and then it decays. Okay. Now, so what I'm arguing is that if you want to compute the entropy or some other special quantities that are not sensitive to this region, to the alpha prime correction, you can actually do that. That doesn't mean that that this action actually capture the correct geometry of the correct modified geometry. It captures some aspects of it, which are enough to calculate some quantities.
For instance, I didn't know why I should believe you're acritical, right? Because that depends on coming in from infinity with some very special amplitude of the condensate. And then, you know, if you miss by a little bit, you go zooming off to infinity. So the
Right.
alpha prime corrections presumably
But what
are very delicate.
I know, but what's interesting is that this simple effective action actually calculates correctly that that amplitude, right? And as you get closer to the amplitude, the place where it's sensitive gets pushed to regions where the curvature is very small. And so there is some kind of an attractor mechanism that goes to this asymptotic solution. And that's probably why it gets the amplitude correctly.
How much does the region at negative rho contribute to this integral of chi-squared?
You can see that. So, right, so phi is increasing. So there is e to the minus phi is killing it. And so in this case, if you look at the integral, I have a picture. It's on the negative side of 0, reasonably close a few string lengths when h is already small. So that region where the corrections could happen, chi is not that large there, and it doesn't contribute much.
Okay, maybe one more quick question, and because
So
we have
you
a
just-
discussion session that
But
starts.
there are many more.
But a quick one. So you had a slide where you say you were computing this acritical just from the CFT, not from this.
No, so what I said is that we looked at the solutions, numerical solutions of the field theory, of the effective field theory, and we discovered that there is an acritical, and we actually discovered that it's e to the minus gamma over 2. And then my expert collaborator who spent their lifetime working on this SL2 cross U divided by U1 theory actually calculated that that amplitude and found that it is equal to e to the minus gamma over 2. So
it's a very naive question. The Goldstone mode of this winding state in the phase, does it play any role, or
yes,
is it a modulus? Or
yes, I didn't discuss it. It's very important because it actually it's related to a component of B mu nu, which I didn't include. And it's crucial for the symmetry properties, the U1 symmetry, the U1 winding symmetry. So, but here I didn't use it. But it's important to keep it in mind.
Okay, in view of time, I suggest we thank Ramy again, and we'll have a short break and reconvene in 10 minutes for a discussion session.
Just for the dinner. So we have, I mean, everybody who sent, they're coming to dinner, the places are there, and I think we have a few more empty spaces. So, you know, basically we have, so, you know, everybody who wanted to come to dinner can come to dinner. And some people haven't answered, but okay, hasta la vista.